welcome to the last week of Gravitational Physics Relativity Lectures. And so the last time, I did it very quickly, and I assigned this, well, I did it that way on purpose, so that actually you have something to do in your homework, but I'm giving up more and more clues to you. So what we are doing is that we are discussing linearized gravity, meaning that you basically decompose the metric tensor into the flat metric plus some small perturbation. Of course, this will be valid in some coordinate system. And so once you do this, you neglect all the terms which are of the higher than linear order in h mu nu. And then you plug this to the general relativity machinery and you calculate what the inverse metric is, you calculate what the Christoffel symbols are, you calculate the Riemann tensor, which is gamma gamma minus gamma gamma plus d gamma minus d gamma. Of course, the gamma gamma term, because each gamma is already linear in H, the gamma gamma term will not contribute to Riemann, and that's why the Riemann is actually relatively simple, as written over here. And so now this is important for your homework. Of course, now you can construct the indices, you can form the Ricci tensor, and then you can form the Einstein tensor. And so this is the result for the Einstein tensor. And you see that the result is pretty nasty, but it's actually reasonable. And so it has, how many terms? 6 terms here. But you can actually reduce it by half by simply going to a new variable h mu nu bar, which is h mu nu minus 1/2 h eta mu nu. And if you do it, then the Einstein tensor actually will have many less terms. And so this simplifies in terms of the new variable. So now there's the time to use the gauge freedom which you have in gravity. So you can do any coordinate transformations. So in particular, I'll be considering x mu to going to x mu minus psi mu, where psi mu is some small vector. So people sometimes write epsilon, as maybe we did in our assignment, but here I simply treat psi mu as already infinitesimal. All right, and so if you do it, then your perturbation transforms in the following way. It's almost like the Killing vector equation, but the linearized one. So psi is already small, so I can replace the covariant derivatives with the partial derivatives because gammas are also small, and so this is of the order of small square. So we are just writing the partial derivatives here. And so now it will be in your homework up to you to convince me that this actually allows you to impose this divergence gauge. So divergence on h mu nu bar equals to 0. So now this is an analog of the Lorentz gauge in electromagnetism. It's just d mu a mu equals to 0. But it's also sometimes called harmonic gauge or the Dundas gauge. So they are all the same thing. So why harmonic gauge, we will see in a minute. But basically, whatever the gauge you are imposing, you are restricting your coordinate transformations, right? So in general, I have general coordinate transformations, which I can do. But now if I am fixing the gauge, which means I am fixing the types of coordinates I can use. And you'll see that this thing actually basically translates into that box on my x mu coordinates has to be equal to 0. So I can only have such coordinates x mu which satisfy box on x mu equals to 0. Okay, so anyway, so this is a very convenient gauge. Well, not really, but yeah. And in this gauge, you have this beautiful form of the linearized Einstein equations. Box on h mu nu bar is minus 16 pi g t mu nu. Okay, so it's instructive to look at what happens if you consider the Newtonian limit. So in the Newtonian limit, you just take t mu nu. So you would have the general structure is the energy density, and then you have energy flux or momentum flux here, and the pressures here. So now we are saying in the Newtonian limit, the most dominant is just the energy density. It's basically like a static limit, so nothing is really moving. So that's why the energy density flux is equal to 0. And also you have small pressures because the pressures are always suppressed by c squared or something like that. So this is also 0. So this is really the rest energy is the dominant contribution to your t mu nu. And then you can show that these linearized Einstein equations, they simply rewrite as your favorite Poisson equation. And then you can show that equally your geodesic equation gives you just the Newton law. So this is the gravitostatics, which we just recovered. So the next order would be to consider that, yeah, I still have small pressures, but now I can have slowly moving sources. So I'll be expanding. So J is small, but I'll be expanding to the linear order in J. So to linear order in velocities. And then you can show that if you look at the component nu equal to 0, so you have h mu bar nu equal to 0, and then you call that F4 potential A mu, then the linearized Einstein equation simply rewrites as box on A mu 4 pi J mu, and this is our Lorentz gauge condition. So you see that you just recovered the Maxwell's field equations. Okay, just recovered. So the Maxwell equations, if you want, are sort of contained in general relativity in Einstein equations. Moreover, if you now take a static field limit and you consider your geodesic equation, you find that your Newton's law get modified by this -4 times B cross B term, where B is constructed out of A mu in the standard way, and so is E. And so you see that you almost recover the Lorentz force law. Okay, so apart from this factor -4, so you know these things also know about magnetism, gravitomagnetism, and so these are called gravitomagnetic equations. They have Maxwell equations plus basically the Lorentz force law. Okay, and you see that it's only this -4 which makes it slightly different from the Lorentz force law. But of course, if we have this analogy with this electromagnetism, and we know that in electromagnetism we have electromagnetic waves, it's natural to expect that also here we have gravitational waves, and it's directly obvious from the linearized equation. So even if we set the sources T mu nu equal to 0, we still have a wave equation acting on our h mu nu bar, and so there should be a corresponding wave solution. So are there any questions to this? No? So chapter 5, applications. Applications. And the first application will be gravitational waves. So part A is gravitational waves. And okay, before I go to that, I told you have this Lorentz harmonic gauge condition, and I just said it. So, but anyway, so this thing is as I define it, but you can show that this is the same thing as if you do G alpha beta equal to 0. That's another equivalent way, which Neil for some reason really likes. And so that's completely equivalent to this condition. But there is even nicer way, well, not really, is that box on x mu equals to 0. So that's why the harmonic coordinates you have. So this is the covariant box. So nabla square on x mu equals to 0. Okay, let me write nabla square on x mu equals to 0. So that's why it's the harmonic gauge. So all three things are equivalent. And so you'll be asked in your interview to show that they are equivalent. But it's very simple. So for example, if you start with this thing here, you know what the gammas are in terms of the h mu nu. So of course I'm linearizing everything, and then this immediately will fall out. And then you can ask, how the covariant box acts on a scalar. And so if you have this condition here, you will see that the covariant box basically reduces to the flat box, just with the metric eta mu nu. But then if you have flat box acting on x mu, well, it's just d over dx nu, d over dx nu of x mu. So the first d nu on x mu gives you delta, and the other derivative kills this delta and gives you 0. Okay, so that's the way how to prove it. So think about it. It will be an interview question.
Sorry.
Yes.
Nabla squared, is that still is it still box but a Euclidean metric?
So this way how I define it is, this thing, G mu nu, nabla mu, nabla nu. So when it acts on a scalar, the statement is this can be written as eta mu nu d mu d nu phi or something like that. So it's just so the statement is in this gauge this is true, and then if I take scalar to be a x mu coordinate, then this thing will follow. Okay, try to think about it. All right. So now we look at the linearized equation. So linearized Einstein equation, and then without sources. Of course, gravitational waves will also exist with sources, but I can set the sources to 0. So you have box on h mu nu bar equals to 0. But of course, I can trace this equation. So if you trace this equation as eta mu nu, then you have box on h bar equals to 0. And then if you look at how h mu nu is related to h mu nu bar on that blackboard, it immediately implies that box on h mu nu is also 0. So basically like going from Einstein tensor for vacuum solutions to Ricci tensor. That's what we are doing. So this is our Einstein equations without sources. And then we may seek a solution which is of the form of the gravitational wave. So seek solution which can be written as h mu nu, which is some constant, and then e to I k dot x, so k alpha x alpha, where this thing is a constant thing and it's called polarization tensor. And of course, this is just one special solution. And if I wanted the complete solution of this thing, I would have to make the sum over all these k modes. I would let epsilon mu nu depend on k, and then I would basically have the Fourier transform. All right. So, but anyway, so that's our ansatz. Of course, this is complex ansatz as any plane wave solution is, and so in the end, you'll have to take real part if you want to have real metric. Okay. So now, if you plug it into this thing here, so this thing, this box here is just a flat box. It's just eta alpha beta d alpha d beta. And so each derivative will just bring me the wave vector k down. And so what you will immediately find from this equation over here is what? So plug to Einstein equation here. And so each derivative brings me just k alpha. And then if I apply again, it will give me another k alpha. So it gives k squared equals to 0. Okay, so we are learning that you can have solutions like this, provided that the wave vector satisfies k squared equals to 0, which means it's a null vector, which we can translate the fact that the gravity waves propagate at the speed of light. So by the way, was a lot of misunderstanding about the gauge fixing in the early days of general relativity. And so although Einstein predicted gravitational waves, very soon after his, I think in 1916 probably, after he formulated general relativity, then he calculated everything you can calculate about gravitational waves. He calculated the power produced in isolated systems, which we'll calculate today, and he predicted that they move at the speed of light and that they are whatever. And so then people were really unhappy about this gauge fixing, and they couldn't understand what was really going on. And then so famous physicist said, well, maybe gravitational waves do not propagate at the speed of light, but they propagate at the speed of thought, because actually this gauge fixing doesn't make any sense. And then Einstein himself, actually in 1930s, wrote a paper that gravitational waves do not exist, and that it was a big blunder of his life again, that he actually predicted them in 1916. But fortunately for Einstein, I was told that actually this went to a journal and went to a referee who actually did understand general relativity. And the referee wrote back to Einstein, this is all nonsense because of this, and that. And you should consider, publishing that paper. Of course, Einstein first got really mad and then said, I send you the paper to publish, not to send it to some stupid referee. But then actually he thought about it and he withdrawn the paper. And so actually gravitational waves do exist. Okay. So very good. So that's the history of gravitational waves. Of course, the biggest event happened a couple of years back when we finally discovered them. All right. So now we can use this. So as we wrote it here, our ansatz h mu nu, the polarization tensor at this stage has, in general, it has to be symmetric, but it has 10 components. Okay. And however, that's of course not true. We know that the gravitational waves should have only 2 degrees of freedom. And so then there must be a way how to fix these 10 components to make only 2 independent. Okay. And so the most stupid way is actually to use this gauge here, which I'll do here because but I never was convinced really that it really fixes the 2 degrees of freedom. But you will do another way, so-called light cone gauge fixing in your tutorial tomorrow, which I think is very, very explicit. And then there is a very elegant way how to do it differently, and that's SVT decomposition, scalar vector tensor decomposition, where you decompose everything into nice pieces which behave like scalars or vectors or tensors and whatever. And you will do it in your cosmology review course and a cosmology exploration course. So that's why I'm doing this most stupid way. So fixing polarization tensor. All right, so we want to show that only 2 true degrees of freedom exist. Okay. So now we have this harmonic gauge. So harmonic gauge which is this partial mu h mu nu bar equals to 0. So h mu nu is this thing here. So again, what this thing actually does is that if you differentiate once, it brings me k. But now this has the same index as mu. So it gives you that k mu h mu nu bar, or epsilon mu nu bar. Oh. Okay. Sorry. So the difference is that here I have h mu nu, and there I have h mu nu bar. So I have to write my h mu nu in terms of h mu nu bar, and then minus 1/2 h bar eta mu nu. And so then the condition which you get is k mu epsilon mu nu minus 1/2 epsilon k nu equals to 0. Okay, so this is the solution for my actual metric perturbation, but my gauge is written in terms of the h mu nu bar, and the relation is over there. So this is the equation which you are getting. So in any case, this is just 4 equations which restrict what my epsilon mu nu can be, right? So this restricts 4 components of my polarization tensor. So now we are down to 6. And so this gauge was the same thing as prescribing the nabla square on x mu equals to 0. So then there is still a residual freedom. So you can still do x mu to x mu minus psi mu, as long as nabla square on x mu equals to 0. But if I am doing this, so this is my x mu prime, which is x mu minus psi mu, and I demand that this thing, x mu prime equals to 0. If I demand this, and my original coordinate satisfied nabla square on x mu equals to 0, so that means I also have to have nabla square on psi mu equals to 0. Okay, so as long as nabla square on psi mu equals to 0, we can still do extra coordinate transformations. So now the argument is that now you take x mu, again, you do basically the Fourier transform. So you do x mu tilde, and then you do the same Fourier decomposition, x alpha, k alpha. So this is what I now do. So I write my old x mu, psi mu's in terms of psi mu tilde, and then the exponential. So now if I plug it here, you find that this condition will be automatically satisfied. So nabla square on psi mu equals to 0 is automatically satisfied. For any psi mu tilde. I hope this is correct. So now, if that is true, you still have at your disposal basically 4 numbers psi mu tilde. Okay, so I actually have still 4 independent things. So still, that means still have 4 functions at our disposal. And so we can do epsilon mu nu to epsilon mu nu plus I k mu psi mu tilde plus I k nu psi mu tilde. So that's the gauge transformation. So that's h mu nu going to h mu nu plus partial mu psi nu plus partial nu psi mu, but now in this k space. And of course, I can arrange that I choose these epsilon psi tildes so that I can eliminate 4 more epsilon. So can eliminate 4 more epsilon mu nus. Okay, so that's the statement, is that really if you are using this Lorentz-like gauge, well, that immediately fixes 4 components of epsilon mu nu, but there is still this residual freedom, and that allows you to fix another 4. But I would say that this is slightly counterintuitive. It's true, but it's not so obvious, at least. Well, okay. So anyway, so we have only 2 degrees of freedom. But as I said, better way to do this, better way, at least much more convincing way, is the light cone gauge, which you'll do tomorrow in your tutorial, or this SVT decomposition. Because so this is very, very explicit. The light cone gauge is very, very explicit. You really see which components you are setting 0, what you are getting, how your equation is decomposing into whatever you want. And this one is very, very elegant. SVT decomposition is very, very elegant. All right. So then the statement is that I can really use these things to eliminate 8 components of epsilon mu nu. So specifically consider a wave propagating in x direction. So that means that your wave vector k mu is k 0, 0. Okay, my t, x, y, and z, and my wave is propagating in the x direction. So then you can show that really you can use this thing here and that thing over there to actually write your epsilon mu nu in the following form. So it's 0 everywhere here, and then it's 0 here, of course, because it's symmetric, but it's also 0 here. And so the only non-trivial components, if your wave is propagating in the x direction, will be in y and z directions. And you can do this thing. And these are your two polarizations of the wave. So you have only 2 components which are independent, which are epsilon 2,2 and epsilon 2,3. And the whole thing looks like this thing here. So you see, if you look at the form of this, then your wave is transverse, right? So I'm propagating in the x direction, by my only perturbations of the metric h mu nu are in the y and z directions. So this is a transverse wave. But you also see that if I take a trace of this thing here, if I look at the diagonal, I get 0. So this is traceless. So it's traceless. So that's why it's called transverse traceless gauge. Transverse traceless gauge. So the only thing are happening in the y and z direction, and moreover, trace of my polarization tensor is equal to 0. So I just want to stress one thing. So to impose this Lorentz or harmonic gauge, you can always do it. You can always do it in the presence of the sources as well, right? So if I have sources, nevertheless, I always can do this Lorentz gauge. So now this gauge is not traceless. Why not? Because our h mu nu has h there, or our h mu nu bar has h bar there. So now this gauge, this Lorentz harmonic under gauge, is also sometimes called the reverse trace gauge or something like that. Because if you look at how you define h mu nu and h mu nu bar, if you take trace of h mu nu, you get h. If I trace this, you get h. But if you trace the other one, you get minus h. So actually, if you take the traces for the variable h and h mu nu bar, you get a minus thing. So this is reverse trace gauge or something like that. So anyway, so this I can impose, the Lorentz gauge I can impose always, even in the presence of the sources. However, this residual gauge here, so explain this thing here, is only true when you are in vacuum. Okay, so only in vacuum I have 2 true degrees of freedom. If I am not outside of vacuum, I couldn't do both things. I couldn't do transverse traceless gauge. So this is only in vacuum. Which of course makes sense, right? We are trying to identify 2 degrees of freedom of a field on its own, right? So as the gravitational wave propagates, we don't need any sources, and we are asking how many independent degrees of freedom this wave has. Okay. all right, so now people don't write epsilon 2, 2 and epsilon 2, 3 because it's too long. And then instead, they write epsilon plus. So instead of 2, 2, they write plus. And instead of 2, 3, they write cross. Okay, and so we have two polarizations. One is the plus polarization. And the other one is the cross polarization. So now you might be interested in, what these polarizations actually do when the gravitational wave passes by. And so the best way how to illustrate what's really happening is the space-time as the wave passes by is to consider ring of test particles. So I can have like a ring of test particles. So I know that the gravitational waves is, let's say, propagating in x and in x direction. So then the only thing which will be interesting is how this thing depends on y and z direction. So I start with a ring of particles, which is a circle. And then as the gravitational wave passes by, so this is at, let's say, t equal to 0, then what we will see is that the effect of the plus polarization is to simply squeeze this like that, and then pump it back again and squeeze it in this direction. So in t equal to 1, it will look like this, t equal to 1, and then in t equal to 2, it will be again a circle, t equal to 2, and then in t equal to 3, it will be squeezed in this direction, t equal to 3, and then in t equal to 4, it will be again a circle, and you keep going. So what it's really doing is just like squeezing then, and then squeezing there, and squeezing here, and squeezing there. Okay, so that's how the plus polarization works.
Is the area conserved of the?
Yes.
Yes. That's the traceless part, or?
Should be, but it's definitely conserved. Yeah. All right. So now the cross polarization. So this was the plus polarization. So now the cross polarization is doing basically the same thing. So now the cross polarization is doing the same thing. So I again start with a circle here, but now the whole thing is twisted by 45 degrees. Okay, so instead of having like the straight up thing, you are having this thing like 45 degrees twisted. And then you come back again here, and then this is 45 degrees twisted, and then circle again, and so on. So this is the cross polarization. So it basically behaves exactly the same way, but now everything is 45 degrees twisted. Okay, so really, if I have ring of particles, but of course, what this tells you is, that as the gravitational wave passes by, it really squeezes the space-time and stretches it in the other direction, right? So really, this is telling me how the space-time itself is actually getting squeezed. Any questions? Yes.
How do you know that gravitational waves is not an artifact of change of coordinates? Of course, we know that we detected gravitational waves, but how people were convinced that gravitational.
Well, exactly. Einstein wasn't, right? So yeah, it's really difficult to understand, whether this is only like what the descent angle, whatever the diffeomorphism is doing for you, whatever the general transformation, I can mimic this general transformation to whatever the true degrees of freedom are. And this is really confusing, but here I really I fix the coordinates. So now I am using fixed coordinates, and so if I see, so I completely fix the coordinates sort of, and so now I still see some effects in these coordinates, but the coordinates are completely fixed. So this must be a physical effect. So that's basically the statement, right? So you have to fix the coordinates, And then if you still see something happening after you completely fix the coordinates, then it's a physical effect. And that's what's going on here. Was another question?
This, so for the most recent stage, you need to be in vacuum.
Yeah. So this thing here, I'm studying gravitational waves in vacuum.
But doesn't the wave itself
I don't understand that.
energy, in which case the energy momentum?
Aha. That's a very good question, very complicated one, of course, very good. So of course the gravitational wave carries some energy, which is very hard to localize, but anyway, it does carry some energy. And so you know that if something has an energy, it should also self-gravitate and produce some secondary effects. So that's right. So that should also, curve the space and, do things. But of course, this is of higher order. So we are here linearizing everything. So we only deal with the linear perturbation, right? So the self-gravitation of the gravitational wave itself will be of higher order. But the statement and what is true is that here we just study gravitational waves in this, perturbative sense. But there are some exact full nonlinear solutions of Einstein equations which describe gravitational waves. And then, of course, the effect is non-trivial. The self-back reaction is non. So this also, comes to the fact that if you write down the vacuum Einstein equations, right? So we are saying G mu nu equals to 0. So we are setting T mu nu equal to 0. So we don't have any sources. But this is really, really misleading. So we are saying that, so remember that T mu nu is for the matter, right? So we are saying there are no matter sources in vacuum spacetimes. However, of course, this still allows you to have non-trivial gravitational fields. And these non-trivial gravitational fields, they self-interact, right? So writing G mu nu equal to 0 is that you have some weird configuration of self-interacting spin-2 field, and that carries lots of energy. And so even in vacuum, you have really lots of energy momentum, actually. But it's the energy momentum of the gravitational field. It's not the energy momentum of the matter itself. All right, so how would you derive this? I think it's instructive because we discussed that in length. So to prove this, proof of this. So what you can say is that let's place a center of the circle, and so the center of the circle is not doing anything. So the center just stays. And so that's why it has the velocity, which is just 1, 0, 0. So that's my center. It's just moving in time. It's not doing anything. And then I measure whatever is happening with my particles around this. But of course, the particles move on geodesics, right? So I don't have any other force than the gravitational force here. I have only the gravity wave passing by. So all these things actually move on geodesics, right? So the particles move on geodesics. And so what we really observe when we observe the squeezing of these things is that we observe the geodesic deviations, right? So how one geodesic is moving with respect to another geodesic. And so that's the squeezing. Okay, so we observe geodesic deviations. So then the geodesic deviation equation is just d square delta x mu d tau square equals to r mu alpha beta nu x dot alpha x dot beta and then delta x nu. So this is what we derived from a couple of lectures back. So delta x mu is the deviation vector. So really it measures where my particle is with respect to the center. So the center is on one geodesic, and then I can measure the other particles with respect to this. So this is my deviation vector between the geodesics and the Riemann tensor, and then the geodesic for the center. But the geodesic of the center is just 1, 0, 0, 0. You can arrange that, right? So now, because this is only non-trivial in the t component, right? So this, okay, first of all, the geodesic deviation is already small, delta x mu, and the gravity wave is very small. So again, the gammas will be very, very small. So if I only want the linear order effect, I can just replace these covariant derivatives with the partial derivatives. Okay? So then I have that d square delta x mu over d, and then tau is t. Again, I don't have to distinguish tau and t, so d square delta x mu over dt square, and this is r mu, but alpha can take only t index. This will be r mu dt and then nu delta x nu. Okay, so this is how it actually simplifies. Everybody happy so far? So now I have to calculate this r mu dt nu. Okay, so fortunately we have the formula here. So we have r mu, and then we are plugging nu and rho to be tt. Okay, so nu and rho is tt, so I will have two derivatives of the metric. And then I'll have terms with one derivative of the metric. So we are using this formula here. So you have r mu tt nu is 1/2 dt square h mu nu, that's the first term. And then we'll have plus d nu d mu h tt, and then minus d nu dt h mu t, and then minus d mu dt h nu t. Okay, so that's that formula in action, but now for our geodesic deviation. Well, for these components of the Riemann tensor. So far, so good. So now we want to, so of course, h mu nu is our perturbation due to the gravitational wave, right? So h mu nu is our wave, which is described over here. So it's h mu nu is epsilon mu nu and then e to ikx, right? But h mu nu has only components which are in the y and z. It's only these epsilon plus and epsilon cross. So plugging this form for epsilon mu nu, you see that there is no component htt, right? So it's not transverse traceless gauge, but there's also no component h mu t, right? Because that's the first row. So this, okay. See, there is no h mu t, right? So this term is not there, and there's no h nu t. So all there is this 1/2, and then two derivatives of h mu nu. But of course, h mu nu will have only y and z components. So this is 1/2 d squared t h mu nu. Well, and so this is it, right? So our equation is d square of delta x mu dt square is 1/2 delta x nu, and then d square over dt square h mu nu. Okay, so this is how our geodesic equation looks like. Any questions so far? Everybody happy? So we just use the formula, so now we can delete it, right? We don't need it anymore. So now, of course, what you want to do is to solve this thing. And again, you can solve it only perturbatively to the first linear order. So in particular, we know that our delta x mu, well, the only thing which is happening is in the y and z directions. Okay, so it will be 0, nothing is happening in time, nothing is happening in x, and then there will be delta y, and then there will be delta z, right? That's how our delta x mu looks like. So as the gravitational wave passes by, it only squeezes y and z direction. Okay. So then let's write that equation for how it looks like for delta y and for delta z. And so specifically, let's consider first the plus polarization. And so for the plus polarization, okay, so we have d square of delta y over dt square. So if we have plus polarization, our metric is diagonal. So if I'm saying we have plus polarization, I'm setting epsilon cross equal to 0, and then I have only diagonal components, epsilon plus here and minus epsilon plus here. Okay, so that's what I'm setting is epsilon cross equals to 0, and I have only epsilon plus. So then, because the metric is diagonal, then h mu nu is diagonal, so there'll be only 1/2 delta y, because it is diagonal. And then we have d square over dt square, and then epsilon yy is just epsilon plus e to I k times x. All right, and then you can write the same thing for the z direction, dt square, and it's delta z. But now my wave, hzz, is minus epsilon plus. So it's d square over dt square, it's minus epsilon plus ekx. Right? Because I'm now using the other component of my epsilon mu. All right. So we have two differential equations. And as I said, all you need to do is to solve them perturbatively. And it's easy to convince yourself, starting from the solution, that this is a solution once I present it. So then you can find is that the solution is solution to leading order is that delta y equals to 1 plus 1/2 epsilon plus e to I kx delta y of 0, and then delta z is 1 minus 1/2 epsilon plus e to I kx delta z 0. Okay, so the solutions are exactly the same solutions, except because I have traceless property, I have 1 plus, and then I have 1 minus here. So in other words, if, let's say, the y component is getting bigger, the z component is getting smaller, and vice versa. And so that's precisely corresponds to the squeezing, right? So y component is getting bigger in one case. So for example, I'm making y component big here, but the z component is squeezing down, and the vice versa. So that's why you can actually plot these solutions, and so this is what you will get. Okay, so to derive this, of course, derive the other one is now you would use the cross polarization, right? But the cross polarization is the metric is no longer diagonal, so it will mix y and z directions, and so that's why it will basically rotate the picture by 45 degrees. So it's doing the same thing, but now with the mixed y and z thing. So that's why it's doing this. You can do it yourself. Just write down whatever the equation is here, but now with the cross polarization, you will get again two equations. You can solve them to the leading order, and you will see that yeah, it's something like this, but now 45 degrees rotated. Questions? So now we understand gravitational waves. So the gravitational waves simply propagate at the speed of light. We can choose them to propagate in the x direction. And then in our transverse traceless gauge, all they do is that they deform the space-time in the y and z direction. And they have two polarizations. One is deforming this way, and the other one is deforming that way. Okay, so that's all there is about gravitational waves. And of course, that's what you measure in LIGO, right? You measure the squeezing of the space-time. You measure, how much the space-time gets smaller in this direction and longer in that direction. Okay, so that's how you measure these things. So just a remark is that if you quantize the theory, so you have the classical theory, of course you can quantize it, whatever. You expect the corresponding particles carrying this force, gravitational force, and these particles are called gravitons. And you will hear that graviton has a spin 2. So how you can immediately recognize this from knowing the polarizations of gravitational waves, you can sort of predict, by knowing what is the classical solution for waves, you can predict what the corresponding spin of the particle is. So y spin 2 so for the graviton, and there's a general statement is that spin s is related to the angle theta under which the polarization modes are invariant, under which the polarizations are invariant by, so you calculate the spin of the quantized particle of the graviton, and it's simply the formula is that you get 360 degrees, and you divide by angle, which leaves the polarizations invariant. All right, so let's look at this polarization here. So for example, well, this doesn't tell me much, but this one here, I have this oblate shape. So what degree I have to rotate it so that I get the same thing? So if I rotate 45 degrees, okay, if I rotate 90 degrees, I get here. Right? So I just listed like that. And if I rotate 180 degrees, I get back to the same shape. Okay, so for gravity theta equals to 180 degrees, which means that the corresponding particle has spin 2. On the other hand, if you had the electromagnetic polarization, actually you have to rotate the whole 360 degrees to get back to the same thing. So for example, I have linear polarization. So to get back, I need 360 degrees. So similarly, for electromagnetism, you would get that theta is actually the full 360 degrees. And then you will predict that the electromagnetism actually has spin 1. If you have a spinner, it's more complicated. You have to actually rotate it twice all around the whole thing, because if you rotate it only by 360 degrees, you get a minus thing. So for, well, spinner, theta is 720 degrees. So you get spin 1/2. So this is really a nice way how you can, cheat by not doing any quantization, not doing anything, and you just look at the waves and look at the symmetries of these waves and what you have to do to get the same thing. How much you have to rotate the corresponding wave, and then you just read what the corresponding spin would be. So now, okay, questions? Yes?
How to imagine the spin error?
Oh, right. So I don't know. I don't have any imagination, but yeah, there are some tricks. I think there are some visualization of this thing. What you need to do. I think it involves a chair and something. So yeah, it can be visualized, but I don't remember how this is done. So really, so mathematically, this is what you have to do. You have to rotate by 720 degrees. But there are some useful visualizations of this thing. But I just don't remember how this is done.
The Mobius strip.
Huh?
The Mobius strip, for example.
Okay, that could work, yes. But there was some nice visualization, like you take a rope and you bound it around a chair, and then some things you have to do, some operations with the chair, and then it shows that it's 720 degrees.
But in electromagnetism, for example, the wave solution is not a perturbative solution, it's an exact solution, right? And in here, this spin 2 is just, we know it's just valid in the perturbative regime, in the linearized.
Exactly. It's a very, very good point. So it doesn't make sense to actually say that gravity really is a spin 2 theory, because all we are saying here is using that we could write the metric as a perturbation around the flat metric. So certainly gravity reduces to a spin 2 theory on a flat background, right? But then once you are in curved space, like highly curved space, it doesn't make sense to actually decompose onto some basic metrics plus perturbation, because what is this basic metrics for general curved space, right? And so then actually this interpretation doesn't. So what is really the correct statement is that gravity does reduce to spin 2 particle on flat background, but so that actually people like to think about gravity like a self-interacting spin 2 theory. But if you are really in high curvature spacetimes, interpreting a spin 2 doesn't really make sense.
If you go to second order, is this still true? The spin 2?
Go to second order, you get gravitational waves. Corresponding energy momentum. Then you get self-interaction of these things at the second order. We will discuss that tomorrow. But yeah. So then you get sort of still spin 2 living on flat space, sort of, which is now self-interacting. But then to get the full GR, actually you have to have infinite number of corrections. You cannot go to second order to third order. You have to go all the way, and you have infinite number of correction terms to get to Einstein equation.
People can manage to estimate the energy carried by gravitational waves.
We will do it tomorrow. Look forward to it. Okay, so now final remark, just following Sean Carroll's book, this is really nice, is that you can look at the vibrations of closed string. Okay, and so you have 3 fundamental vibrations, the 3 simplest vibrations of a closed string. So this is my closed string, you start with a circle. And so you have sort of like 3 polarizations. So this is how you start. And so one possibility is that the whole thing is sort of moving up and down. So later I'll have bigger shape. And then later I will have smaller shape. So this thing is going like this, going like that, going like that, going like that, going like that, going like that. So it's basically, so this is called breathing mode. And so it's really, the circle is just getting bigger and smaller. So now the area is not conserved, of course. And you can show that this corresponds to spin 0. And then you have 2 other modes. One of them is like this. So again, we are going this way, that way, this way, that way. So precisely, basically, whatever the plus polarization is telling you. So you are now preserving the area, but you are squeezing that or getting longer. Or you have that breathing mode. Okay. So you have these two modes. Of course, they correspond to spin 2, which are like plus and cross polarizations. Okay, and so what this is telling you is that if you have actually closed relativistic string, then it behaves. Well, these vibrations describe sort of particles, and so the fundamental vibrations will give you a spin 0 particle, a scalar, and they will give you also spin 2 particle. It will give you the graviton. So from string theory, you get a scalar, which is called dilaton, plus massless spin 2, which is graviton. And so that's why actually string theory is a theory of quantum gravity. It's not the theory of quantum gravity, perhaps, but it's a theory of quantum gravity. But you see immediately the prediction is that you don't really only get gravitational fields, but you also get this scalar field, this dilatonic field. In addition to that, which is, however, not really observed, so far, which doesn't prevent people to study what would happen if we had the dilatonic field. And so, for example, people study what would happen, what would be the prediction of gravitational waves if you had, for example, the collisions of black holes with the dilatonic field. Okay, and so for example, Louis Lehner is now studying heavy numerics, doing like really, if the string theory were correct, and we would have some dilatons in the universe, then what would be the observational effect when you collide the black holes, which also contain this dilatonic field? But so far, nothing was observed, and not good for string theory so far.
Why is it called a dilaton?
Huh?
Why is it called a dilaton?
I don't know. Anybody knows?
The innovation of that thing, maybe?
No, I don't think so. I don't think so. Anybody knows why it's called dilaton? All right. So anyway, it's just to amuse you that whatever you just learned, now you understand the basics of string theory as well. So you understand why string actually is giving you graviton. Right. So now what we would like to do is to actually, so we understand theoretically the gravitational waves, but hopefully these gravitational waves are produced in the universe. And so we are moving more towards astrophysical observations. And so we want to predict, how much and how strong these gravitational waves are when they are produced, let's say, in a collision of two black holes, or if you just have a binary system where one star rotates around another, how much energy the system is losing through the gravitational wave production. Okay. Are there any questions before we go there? So by the way, tomorrow we will have a guest speaker, Louis Lehner, who will tell you everything about gravitational waves. And he's like the biggest expert on gravitational waves. And so hopefully he will give you some nice propaganda so that everybody will actually jump and study gravitational waves after this. Okay. So let me start talking about gravitational radiation from an isolated system. So now what I really have in mind is that now you have some system which is like an island. It may be a binary system, it may be a collision of two galaxies or whatever, but it certainly doesn't extend all the way to the observer. Then you have the observer, that means us, here. And so we observe this in radius r. And then everything what is happening in that system, so for example, this binary thing can be described by some r prime. Okay, and so we are, of course, you'll be studying. So now, something is happening here, and that produces the gravitational waves. And then we are interested in how we observe these gravitational waves at the distance small r, which is much, much bigger than r prime. Okay. Also, we'll be using another approximation that, let's say this thing is orbiting with frequency omega, and then we'll be using the approximation, well, whatever I derive is valid for slow motions, means that the frequency is actually much, much smaller than 1 over r prime. Okay, so for slow motion, of course, this will break down when you are, for example, colliding two black holes. So the first gravitational wave observation, when the two black holes collided, it was like significant number of the speed of light. They collided in the last second, whatever. But we'll see that tomorrow in that Lewis propaganda. All right, so this is what we want to describe, and so we want to describe, how much the gravitational radiation we see very, very far away from the system. Okay, but of course now, if you want to describe the production, we need to include the T mu nu, which corresponds to our star. So our gravitational waves are now sourced by, let's say, this binary system. So we have to really solve. So we have to solve the linearized equation, which is box on h mu nu bar equals to minus 16 pi T mu nu. Okay, again, we are doing that in linearized approximation, which is the first thing to do. But now we have to have source. So source is important. All right. So in particular, we want to find a special solution of this equation. So the general solution is the solution of the homogeneous equation plus a special solution. And the special solution is from our front-end course given by Green's function. And so we take the retarded potentials. And so we write down the general solution here. So the solution, special solution is given by, that's right, by the Green function, where I take the delta source on the right-hand side. But we already did the work. It's exactly the same equation. This is just the wave operator. And so you know that the solution is advanced and retarded potentials. And you disregard advanced potentials based on physics. And so then your solution is h mu nu bar of T and R is equal to, and now the only thing is the factor, but this is 4 times bigger than what we had in electromagnetism, so that's why we have 4. And there's G here as well. So 4G, and then D 3 R prime, T mu nu in the retarded time, and R prime, R minus R prime, and then T retarded is just T minus R prime. Okay, so that's the special solution, which we derived in the previous course, but now we're just applying that to T mu nu. Okay. So this is called retarded time, and it tells you that you have non-trivial field only when the source actually lived in the light cone previously. So I can have non-trivial field here only if there was a source, living on that light cone here. So only that source actually produces the waves, which can hit me here, but not outside of the light cone. All right. So now let's look at this and use our conditions that we have an isolated system, that we are far away from the system, and that the motion is slow. Okay, so let's look at this thing here and specify to our problem. And the best way is to do actually by Fourier transform. Is there a question? No? No? And the best way is to do by Fourier transform. And we are running out of time, but that's fine. All right, so what I will do is that I will look at the Fourier transform of that solution in the t direction. So I'll be looking, replacing t is the frequency omega. So then you have h mu nu omega and r, which is just the Fourier transform of that h mu nu bar. So it's 1 over square root of 2 pi, and then dt e to I omega t and h mu nu bar. T and r. Okay, so that's just the Fourier transform of my solution here. So now you plug in whatever the solution is. Okay, so you know that h mu nu bar is given by this horrible thing. So this is 4g square root of 2 pi integral now over time, but also over d3r prime, and then e I omega t, t mu nu, retarded time, r prime, r minus r prime. So far, everybody is happy with just using the general solution. Now we are going to do a fancy thing. So we integrate over time here. Okay. So now we change the integration over time to integration over retarded time. So instead of dt, I will have dtr, and then there's, well, dt and dtr, the same thing. But I'm picking this thing here. So whenever I see t, I replace it with tr plus r minus r prime. Okay. So from t to tr. Well, very fancy mathematics, 4g 2 pi. So now we have d tr and d r prime 3. So now the exponential will become now e to I omega dr, but also plus I omega r minus r prime, just changing the variables from t to tr. And t mu nu dr r prime r minus r prime. Okay, very fancy mathematics.
Is it not like a Jacobian or something when you?
Oh, the Jacobian is 1, right? So I'm just changing one-dimensional t to one-dimensional tr.
There's a dependence on r prime there as well, though.
Right. Which could depend in principle on t, but that would be a high order effect or something like that. So I'm just neglecting that. Yeah. All right. So now you see that I'm integrating over tr, but the only appearance of tr is here in this exponential and here. So it's just a Fourier transform of t mu nu of omega. Okay, so this thing is just 4g and d 3r prime. This is what is left, I omega r minus r prime. And then you have t mu nu tilde omega r prime r minus r prime. Okay, so I got rid of PR integral by simply saying this is just a Fourier transform of d mu nu. Okay, and then I use again the fact that I'm very, very far away. So r is much, much bigger than r prime. So I neglect this r prime here. I have r. And then I neglect this r prime here. I have r. Okay, so that's just using the fact that r is much, much bigger than r prime. And so to the leading order, this is just for g, and then it's e to I omega r over r, and then integral d3 r prime t tilde mu nu omega r prime. So far, everybody happy? Well, this is what we have to get, right? We are interested in the fields which go like 1 over r, because those are the radiative fields, right? So if you get fields which go like 1 over r square, they will never contribute at infinity because when I integrate over the sphere. So you need really 1 over r fields. And so we are just keeping the leading order thing here in 1 over r. All right. So we have this. The next step is to look at your Lorentz gauge condition. So I told you that we can still impose the Lorentz gauge condition even in the presence of the sources. So this is fine. We cannot just use the transverse spaceless gauge because that's too much for vacuum. That can be only done in vacuum, but Lorentz gauge you can always do. So then note that Lorentz gauge d mu h mu nu bar equals to 0 gives you that if you do the Fourier transform of this thing here, it gives you that h tilde d mu equals to I over omega. By the way, I was trying to recover a sign. Again, the sign doesn't like me. Tilde. So this is in the Fourier space. So I'm just doing Fourier transformation on this Lorentz condition, and this is what you are getting out of that. So just the time derivative translates into multiplication by omega. But I'm not finding this sign. I'm always finding minus sign. But anyway, so what this means is that. So this is just a direct transformation of that. What it means is that I can choose mu equal to t and mu equal to I. So in particular, if you do mu equal to j, then you are finding that h tilde tj equals to I over omega di h tilde ij. Okay, so what it means is that if I know what my Fourier transform of ij components is, then I can also find tj components. Okay, so and similarly, you find that h tilde dt is again up to a sign. It's minus 1 over omega square di dj h tilde ij. So you see that whatever the Lorentz gauge condition has to kill 4 components. In other words, the components htt and htj, so ht mu are given in terms of the components hij. Okay, so only h, ij, tilde are independent. And so if I know these guys, I can find H2 mu from this thing here. All right, so that's a simplification. So we can only look at the spatial parts of this formula here. So we have the formula H mu nu omega r is given by this. So all we need to look at is the spatial part of this thing. All right. So let's look at, and so for that, we need to know what is T3 R prime on Tij tilde is. So look at integral T3 R prime Tij tilde omega R prime is, because if I know what that is, I know what my Hij tilde is. Okay. And then there is a dirty trick. So you can write this by a funny identity. So this is an integral over d prime k x prime I t k j minus integral x I prime d prime k t k j. Okay, so let's look at whether it's true. So I write it as a total derivative of my, put in this is I and j upstairs, it doesn't matter, but let's put it this is upstairs. So if this guy hits x, gives me delta ki, which is Tij, which is whatever I had before, but this guy can also hit, this is the other term, and so I'm subtracting that term here. Okay. So now, however, this is a boundary term. This is a total derivative term. I can turn into the boundary term, but remember that our system is limited. It's not isolated. So if I go outside of the sources where T mu nu is 0, then this thing will be 0. So this gives me 0. Gives me 0 because it's a boundary term. And we have an isolated system. Okay. So the only term which is here is this one here. But this is like a spatial divergence of my T mu nu. But I know that my T mu nu is conserved. So nabla mu T mu nu equals to 0. So I should be able to transfer this into a time derivative of T0 j, right? But the time derivative gives me I omega, okay, because I'm now in the Fourier space. So this thing here is nothing else, and this minus sign is that I omega integral xi prime, and then t tj d3r prime. Okay, so I'm just using the divergence, the fact that T mu nu is conserved. Okay, so you see that what we have done is basically we traded one index I of this T mu nu to an index T and multiplying by xi. Okay, so now the same trick can be done again. So now we want to trade this index j for index t, but of course what we will pick up is the xj term. Okay, so then you can show that this thing is equal to, again, we will be picking up I omega, but there's this miracles 1/2, which you can find in the notes, minus omega square over 2 at integral xi prime, xj prime, t, dt, d3r prime. Okay, just using the same trick again, just, writing it as a boundary term, subtracting something, using the fact that T mu nu is conserved, you can find this thing here. But TTT is the energy density. So what you have here is an energy density times xi times xj, which you probably recognize as something
Quadrupole.
Quadrupole moment, perfect. So this thing here is quadrupole moment. Which I'll denote as A Ij. And so we have a beautiful result, which I'll write here. So we found that Hij tilde omega r is given by, so there's this one minus 1/2, but we had 4g somewhere. So it's minus 2g omega square. And now that integral which we were massaging, and so this is what was standing also before it, I omega r over r, and then Ij. Because TTT rho is as a function of omega, this is actually Iij omega. So this is the Fourier transform of the quadrupole moment. All right, and so now you can go back to the T space. So you now do reverse Fourier transform, and you find that Hij bar T and R is just Fourier transform of this in the time direction. Okay, and so what you find is that this is equal to 2g over r d square Iij dt square, where this is now your normal quadrupole moment in the x space, in the time space. Okay, and of course, you have also this I omega r thing. Well, this is evaluated at t equal to retarded time. This is called quadrupole formula, and it's the famous result. It tells you that the perturbation of the metric, as I see it from very, very far away, only depends on how the quadrupole of the system is changing. So if I have an isolated system very, very far away, actually, I don't care about the mass of the system. I don't care about the dipole moment of the system. All I care about is actually the quadrupole moment of the system. And then two derivatives of this quadrupole moment actually tell me, what is the corresponding weak field, which I see very, very far away. Okay, so that's the quadrupole formula. So now remember, if you studied electromagnetism and you studied radiation, then what would be the first main source of radiation? Would be? Dipole, exactly. So compare electromagnetism to magnetism, where we have a dipole. Okay. If you studied the scalar field radiation, so this is spin 1, right? So this is spin 1, and the dipole is actually the leading order. If you have scalar, then you would actually find that already you have monopole radiation. Monopole radiation. So already, changing scalar mass in time gives you radiation. But now for gravity, the lowest order is quadrupole. So now this is a general statement. If you go for any spins, so the higher the spin, the higher the multipole you have to consider actually contributes to radiation. Okay, so just remember this: for scalar, already monopole radiates. For electromagnetism, the monopole does not radiate, but the dipole radiates, because basically the only thing outside of the electric charge is just electrostatic field. And to change the electrostatic field, you would have to pump some charge inside. So that's why the monopole doesn't radiate, but the dipole does. But for gravity, the monopole doesn't radiate, the dipole doesn't radiate, but it's the quadrupole which radiates. And so that's the connection with the spin. Any questions? Yes.
How do you get the H bar TT components or TJ?
So this is the spatial components of H bar. So now I'm saying that the Fourier transform of these components are given here. Of course, I would have to do the Fourier transform of this. I would have to calculate what these things are. Yeah. But you know, in the end, what really matters is the spatial components, because if you want to study the gravitational waves, the gravitational waves will be non-trivial. Really, there will be HT mu. I can always set equal to 0, so I don't really care if I'm very far away from it. So this is the thing which will really be interesting.
David?
Yes?
Is there any intuition about the why quadrupoles radiate and not dipoles?
Yeah, it's the conservation of momentum or something like that. Yeah, so you know, whenever you have some conserved quantities, you can kill some effects. So for example, I can kill monopole radiation for electromagnetism by conservation of charge. So now you have conservation of mass, but you have also conservation of momentum, and probably angular momentum. So yeah, you can show that these conservation laws actually forbid for the monopole and dipole to radiate in gravity. All right, so I'll see you tomorrow.